Okay. Welcome back, everyone. We are slowly getting into kind of the half of the class, which is interesting. Um, so today we're going to continue talking about pipelining. The last thing that we talked about last time was forwarding and data hazards. So we're going to continue talking about forwarding and data hazards. Okay. Cool. Okay. All right. So if you remember, I told you about the problem of raw data hazard, right? So the raw data hazard was happening when we are writing to a register, and within 2 cycles, we are trying to read from the same register. Um, we talked about one solution for this, and that was stalling. The stalling could happen in hardware or software. In software, you can add no operations to your instruction set. That's typically what we don't do because it has different problems, including increasing the size of your instruction memory and so on and so forth. What we usually do is we implement this in hardware, as I showed you last time. We effectively kind of like uh, freeze the first half of the processor, which is these first 2 steps, and then let the other 3 stages to move forward. But since we have frozen these 2 parts, we replace the instruction that would have gone into the second stage with a no-op. So we let the no-op move forward, and we call this a bubble or no operation. Um, then we uh, then we talked about a better solution to this problem, and that was forwarding, or some people call it bypassing. So the basic idea of forwarding was that an interesting way that you can kind of remove the need for stall is, since I already have the value that I want here, I can then somehow, if I rewire and somehow connect this into the beginning of the ALU, I can basically bypass these values that I read here. So essentially, I read some wrong values, some old values, but I can let that read happens, but I can overwrite it with the value that I generated by the ALU. Okay? And we show that this can actually happens, as I showed you later, um, using this architecture here. So essentially, all we need to do is adding this 2 multiplexer here, this multiplexer and this multiplexer, um, in order to basically override what we have read here. So in original design, we read things from the register file, we feed it into this register here, and then we connect that directly into my ALU. Now we are adding these 2 muxes here, and as you can see, these 2 muxes and here, right? So from here and here, and replacing the value of RS1 and RS2 with those values. In order to decide when we should do this, we have this additional control logic called forwarding unit that basically decides whether the condition for forwarding is applicable in this particular scenario or not. Let's go back and like talk about this a little bit more. Uh, so as I said, the idea of forwarding is that we want to remove the stalling. So we hopefully can just continue normally by doing this. Uh, and important things to remember is that forwarding might happen in 2 cycles. So sometimes you need to forward from this instruction to this instruction. Someone you need to forward from this instruction to this instruction. So you need 2 forwarding basically. And we do this by forwarding from beginning of DM stage to ALU, or beginning of write back stage to ALU. So 2 forwarding happenings. Another thing to remember is that you might need to forward to 2 registers, right? So for example, if this one was also X5, then I need to forward from here to here. I also needed to forward from here to here. Same story here. So I can forward from here to here and forward from here to here. Forwarding could also be kind of changed. So for example, if I have something like add X5, X3, X2, and then I have, let's say, a sub, X6, X5, I don't know, X1, and then I had another, let's say, XOR, X7, X6, X5, then as you can see here, I need to do lots of forwarding. I need to forward from here to here. I also need to forward from here to here. But then there might be lots of forwarding that happens in parallel, but generally the criteria for all of them are the same. Is that there is a destination register that's being written, and within 2 cycles there is a source register. The same source register needs to be read. So I need to design my logic so I can handle all of these cases, right? So everything could needs to be happening in parallel. So essentially, I need 2 forwarding logic, one from the memory stage and one from the write back stage, and I also need a forwarding logic for 2 registers, for RS1 and RS2. Okay. So as I said, so the design of the data path would be effectively, if this was originally my ALU with a mux here that takes RS2 or immediate, and this was my RS1. Now what I need, and this was a mux, now what I need to do is that I need a new mux that takes this old value, but also now takes 2 new values. This one is coming from mem stage, and this one is coming from the write back stage. And now I need a new control signal. This is what we call forwarding control signal. And since I need to do it for both RS1 and RS2, I have what we call forwarding A and forwarding B, which the second one is also the same thing. So this is what comes from here. So essentially, this is kind of connected to here. And this is, again, coming from the mem, and this one is coming from write back, and this one is called forwarding B. So as you can see, I can forward from either memory or write back as I wish. I can also decide to forward to RS1 or RS2 or even both, right? So I have 4 different possibilities that can happen all at the same time, okay? So now the question is, does forwarding fix all the issues that we have? And essentially, by forwarding, can we avoid stalling at all times? The answer to this question is not necessarily, and this is what we call load use data hazard. So for all the ALU operations, for all the I-type and R-type operations, we are good. But unfortunately, for load operations, there is this problem that we call load use data hazard. So here's the concrete example. So let's say I have an instruction like load word X5, 40, and X2. So essentially, it's reading the value that is stored in the address X2 plus 40. And save that value into this register X5. So this is my RD. So now imagine that immediately after this, I have, let's say, an R-type instruction which reads that X5 value and now wants to write it. So now the question is, can I use forwarding for this? So now, so what happens is that the difference here, in this case versus, let's say, for example, if I had add X5, X1, let's say, and X2, the difference between this case and this case is that in this case, the value would have been available here at the end of the execution stage. In other words, at the beginning of memory stage, I had my correct value. But in this load word example, the correct value only is available at the end of the memory stage, right? So I cannot forward. If I want to forward at the beginning of memory stage, the value is not still valid, because the value that I can forward at the beginning of the memory stage is this value, which is before reading the actual content of the memory. Okay? So I cannot forward from here. My option is forwarding at the end, which is kind of the beginning of this stage. By the way, you cannot forward at the end because we need, this will add to the critical path. Because remember, when we do the forwarding, then we need to add this delay as well. And that extend my stage, which I don't want. That's why I only forward at the beginning of each stage so that that doesn't change the latency. So my alternative would be forwarding from this point. But as you can see, this point is too late because I need the value at this cycle, but the value is actually available in this cycle, right? So we are kind of back to the problem that we had without forwarding, which the value is available at later stages, but we want to use it at earlier stages. And again, the reason that we have this for memory and don't have it for something like add is available here, or in other words, at the beginning of the memory stage, versus this instruction here is available at the end of the memory stage. So I can only do the forwarding at the beginning of the write back. And as you can see, this is needed at the beginning of this stage. So we are kind of one cycle late. Okay? So how do we fix this? And then again, remember that half cycle will not fix this issue either, because again, half cycle was useful for reading and writing to the registers. It doesn't work for memory because memory takes the full cycle to read things. It's much slower than the register file, so it takes the full cycle. So what happens is that unfortunately we're not going to be able to do forwarding without stalling. So what we should do is we're going to do what we used to do before. That is, we're going to stall for one cycle. So basically, going to stall here. And then in the next cycle, when the value now is here, now we can forward from here to the ALU operation. So we're going to do this way. So essentially, what used to be load and then sub, now is load, no op, and sub. And now, as you can see, essentially, once load goes here, now at this point, the value becomes ready. So now at this point, I have the correct value. So what used to be sub in this point is now a no op. So the no op goes here, and sub stays here. And now sub can go here, and now we do the forwarding. So we forward from here to here, and now we can continue moving forward. So compared to the previous case that we didn't have forwarding, we save one cycle. So we still do the forwarding to save one cycle, but we cannot do forwarding without stalling for the load use data hazard. Okay? So that's the big difference between load use data hazard and the just regular R-type or I-type data hazard. Okay? So now the question is, as I said, how do we detect when to forward? And if you remember, we're going to have this, what we call forwarding unit to detect that. The condition for forwarding is actually quite simple. You need to basically do these checks. You need to check whether the RD of EXMEM, that is the memory stage, and or the RD of write back stage is equal to the RS1 or RS2 of your execution stage, okay? And then, as I said, you check this for both conditions, right? So you check this for both the write back stage and for your memory stage, okay? And you check it with both RS1 and RS2. So basically 4 check-ins at the same time. Additionally, in order to make sure that this is indeed need to be forwarded, you check that whether this instruction is actually writing to the RD. If this instruction is not going to write to the RD, then forwarding is not going to be needed either, okay? So there's 2 things that we are really checking. We're checking whether RS1 and RD or RS2 and RD are the same. And also we'll check that whether you're going to actually write to that RD. If you're not writing to that RD, again, forwarding is not going to be needed, okay? And these 2 are independent. So if this condition is true, we're going to forward from EX to MEM. And depends that if this and this true, we're going to forward A. If this one and this one is true, we're going to forward B. If all of them are true, we're going to forward for both A and B. Okay? And similar story for the write back stage. So we check all of them and then we forward all of them. So at any case, we can forward 4 things at the same time. Yes? EX is execution. So the question is, what is EX? EX is execution stage, the ALU stage. Okay? And then one thing to remember is if RD is X0 and RS1 is also like X0 or RS2 is X0, you may or may not forward, doesn't matter. If you forward or don't forward, nothing happens. So you can have an extra check here that if this is equal to X0, don't forward, or you can forward. Again, in either case, nothing happens. Yeah. Mm-hmm. So the question is from this one, why don't we delay? So remember, this does not make a decision about delaying. It's just make a decision about forwarding. Okay. So there is another unit that we call hazard detection unit that decides whether or not we need to delay. Okay. So again, as you can see, this does not know whether this is a load use hazard or is it a regular R-type or I-type hazard. It just forwards as it sees it. And again, remember that for load use hazard, we also need to forward. So in either case, we need to forward. It's just a question as do I need to stall and forward or do I need to just forward? And that's a responsibility of another unit that we're going to talk about. Okay? All right, so as I said, this would be the model that we're going to use. That, as you can see, this is basically your RD for EX mem stage. This is the mem stage. And this is the RD of mem WB, the write back stage. So we're going to feed this into my forwarding unit. I'm going to also feed my RS1, RS2 into my forwarding unit. So these are the 4 checks. Another thing that goes into the forwarding unit that we are not showing here is read write, right? Read write of this instruction should also go to the forwarding unit. And if these conditions are true, then we're going to forward, right? So we're going to forward A, forward B, and then decide which one we're gonna use. Okay? And then how do we detect for load use case as someone asked? So load use case is kind of fairly similar. The only difference, so this part is the same. The only part that is different is that the control signal. So if the control signal is mem read equal to 1, that means that this is going to be stall and then forward. Okay. So we need to forward this signal to forward it to the next instruction. Okay. And then how do we do the stalling? The stalling happens with this what we call hazard detection unit. So pay attention that we have hazard detection unit and a forwarding unit here. And the hazard detection unit is responsible for creating the bubbles. I'm going to describe how the bubble works. So essentially, we need to add this muxes. And forwarding units is decide when we are doing the forwarding. Okay? There's also another interesting thing that I'm not going to answer here, but I want you to think about it, that why are we checking the mem read in the instruction decode execution stage? So think about this. I'm going to answer it next time, or we can answer it on campus wire. Actually, when I'm describing the hazard detection unit, you will see that why we're doing this. All right, so let's talk about how do we insert the bubble as well so that we have the full picture. So as you can see, the hazard detection unit, so by the way, first look into what the hazard detection unit takes. So it takes essentially this, again, this RD here. It takes memory detection, control signal as well. And it takes the RS1 and RS2 as well, right? So what it does is basically doing this. So the idea of bubble, if you remember, was for inserting bubble, we need 2 things. One was we need to freeze instruction decode and instruction fetch states. Okay. And the second thing is that we need to insert bubble, which was no op, in EX stage. And then this bubble will basically just move forward. Once I insert it, it will just pass over by itself. Okay, so I need to do these two things. So the first thing we're going to do is that, as you can see, the hazard detection unit has this control signals uh, called PC write and IFID write. These are the write enables. If they are equal to 0, these registers, this PC register and this pipeline register, not going to get updated. In other words, we freeze the instruction in fetch state and we freeze the instruction in the decode stage. If we don't let these two registers to get updated, we keep having the same two instructions here. So for example, if this was a load instruction and this was a sub instruction, if we don't let this load to go to the next stage and this sub goes to the next stage, if I don't update this, this PC will be the same value as previous time. So it will keep reading load word, load word, load word, load word until we let this PC to get updated. And since this register is not also updated, it keeps reading sub. So we kind of keep repeating the same thing over and over for these two instructions. Okay? So that's the first thing that we do. This is the freezing part. The second thing that we do is that we need to push no op into the later stage. How do we do that? We're going to use this very simple trick that we're going to say that, okay, I don't need to kind of like replace all these values with zeros. All I need to do is that I'm going to replace the controller with 0. Because if you remember, my controller was active high, which means that if the values are zeros, nothing going to happen. We're not going to write to the memory. We're not going to read from the memory. We're not going to write to the register file. So what I'm going to do is that I'm going to add this multiplexer, and I'm going to just do the decoding normally. But then if I decide that instead of pushing the actual instruction to the next stage, I want to insert a bubble, I'm going to do this control signal and make this equal to 1 to select this. So essentially, I'm pushing all zeros control signal to the next stage. And as you will see is that once everything is 0 here, there will be operations, but these are what we call a no operation. So there's like all zeros operation. So there will be like subbing two zero numbers together. I'm not going to save anything and so on and so forth. And then this will move forward, right? So as you can see, this is basically moves forward to the mem stage and write back stage and so on and so forth. So inserting a bubble is as simple as replacing the control signals with all zero signals. Okay? So that's the main two things that we do in the hazard detection unit. So if I didn't have the forwarding, my hazard detection unit should have stalled every single raw data hazard, right? So, and it has to stall it for 2 cycles. But now that I have forwarding, I only need to stall the processor if I have the load use hazard. And I only need to stall it for 1 cycle, okay? So that's kind of like putting things together. That I have added this 2 units, hazard detection and forwarding. Forwarding decides when to kind of replace the values here. And hazard detection unit decides when to freeze these 2 registers and when to push a bubble inside my pipeline. Okay? Any questions? Yeah.
Once we replace the control signal.
So the question is, once we are replacing the control signal, what happens to the original signal? Remember, you still have sub here. So in the actual cycle that you really wanted, it just recreate the control signal. So essentially what happens is that you keep doing a redundant work every cycle. Yeah.
The program where you had no up there, does that mean no is just something you made up there and the actual that's happened is just something unexpected?
Correct. So the question is like in the actual sequence of instruction, how does this work? In the actual sequence of instruction, you're not going to see bubble or no ops, right? You're going to see, for example, load word and then sub and then add and so on and so forth. In hardware, for example, we will detect that, oh, this is a load use hazard, so we're going to insert the bubble here. So again, from the architectural point of view, you're not going to see any of these. From the macro architectural point of view, you're going to see this. Any other questions? Perfect. All right. So we're going to switch gear and talk about other types of hazards. Any final question about data hazard forwarding or hazard detection units? Yeah. So the question is, do we have an actual no-op instruction in our ISA or not? Some ISA do have a no-op instruction, but most ISAs don't. But also you can have, for example, you can define the no-op. So you can, for example, say add x0, x0, x0 is equivalent of a no. Okay? Which actually, if you think that if I pass 0, that's exactly what's going to happen, kind of, right? Because ALU op would be 0, 0, and my register is going to be 0, 0, and so on and so forth. All right, so let's, if I remember, I told you that there are two other types of hazards as well. This is what we call structural hazard and control hazard. Structural hazard is rather straightforward. If one of the units that we are using is busy, we're going to have what we call a structural hazard. So for example, if I go back here, remember that this is a pipeline, which means that instruction needs to go to the next step, next step, next step. If for any reason, for example, my register file has not finished the sub instruction, I cannot push the new instruction in, right? So this is what we call a structural hazard. In our design, structural hazard never happens because we always make sure that the clock cycle is more than one stage, the maximum of the stage. We always also make sure that we have enough ports to do things in parallel. For example, if I didn't have two read ports, then it would have taken 2 cycles for me to read a value if it needs two registers. In other words, every other cycle I'm going to have a structural hazard. That's why I added these two ports so that I can read things in parallel. So structural hazards really basically doesn't happen in our design, but keep in mind that, for example, if I want to make the system more power efficient, then I could reduce the number of ports. Then in that case, I need another condition added to my hazard detection unit to basically stall the processor when it needs to read 2 ports register. So for example, if I have back-to-back R-type instructions, then I need to stall. If I have like an R-type and I-type instruction, I don't need to stall, right? Again, this is a trade-off between performance and other metrics, including power or area. But as I said, in most processors, you try to avoid structural hazards, okay? But the more important and more involved problem in pipeline processors is what we call control hazards. Control hazards is when we have control flow instructions. So essentially the idea is that since we are always kind of like filling the pipeline with PC+4, PC+4, there will be scenarios that if the branch is taken, is jumping to somewhere else, we don't know what is the target address and what instructions should be filled. And this is what we call control flow hazards, which actually going to be what we're going to talk about in your 6th module. All right, so let me talk about that. So we're going to focus from the rest of this lecture on control hazards in this particular problem. So if you remember, I showed you this slides in the past, that we are assuming that our memory is linear, right? So for example, again, let's revisit this example. Let's say I have like, a code sequence like this, that I have an if then else. I run some code before this if, and then if the condition is true, I'm going to run the block B. Think about block B as sequence of instructions. And then if the condition is not true, I'm going to run block C, and C again could be sequence of instructions. In either case, at some point, I'm going to converge and continue executing the program. if I draw the control flow graph of this, the control flow graph would look like something like this. So I have a block A. At the end of this block, I kind of have what we call a branch, that if it's true, I'm going to run B, and if it's false, I'm going to run C. And in both cases, I'm going to converge to D. And now again, think about this in terms of the binary code and your instruction memory. Your instruction memory, since it's a linear address, right? So for example, this is the beginning of your code, and this is how you're going to move forward. So every instruction, PC plus 4 instruction, is kind of like here. At some point, you're going to have this branch instruction, so this branch equal instruction. And then you have two choices here, that the immediate next instruction, the following instruction, could be either the first instruction of block B, or it could be the first instruction of block C. It cannot be both, right? So what will happen is that in this case, PC plus 4 would be this block, the beginning of this block. So if I assume that this branch quote unquote is not taken, I'm going to continue with C. But if this branch is taken, then I need to skip bunch of instruction and goes here, right? And this is what we had as control flow instructions. We kind of learned how to design this in ISA and how to generate the offset and all those things. But another question is, how does this run on a real processor? For single cycle, we were okay, because for single cycle, we finished this instruction, and at this point, we know what is our target branch is, whether the branch is taken or not, whether the condition was true. And if the condition was true, let me go back to this design here. Oh, no, I don't have it. If the condition was true, then we jump. Not true, we didn't jump, right? So for single cycle, it was fairly straightforward. But for the pipeline design, that's the issue. Because, for example, let's say I have something like this. I have load word, then I have branch equal, then I have sub, then I have add, okay? Then kind of like lots of instruction later, so this is branch, let's say label, and then label is here, and then I have, for example, here I have XOR, and so on. So now think about your pipeline, right? So your pipeline, your load word goes into the pipeline. That's great. Then the load word goes to the next stage, and now the BEQ kind of comes. That's also okay. Then in the next cycle, load word goes to the execution. So this is my fetch, this is my decode, this is my execution, this is my memory, and this is my write back. So at this cycle, the load goes here, and now branch goes to the decode stage. So now the question is, what should I fetch here? Should I fetch stub instruction, or should I fetch the XOR instruction, right? And in order to answer this question, that whether I should fetch the sub instruction or whether I should fetch the branch XOR instruction, I need to know whether this branch is going to be taken or not taken. If it's taken, I need to fetch XOR instruction. If it's not taken, I need to fetch the sub instruction, right? So I'm going to have this problem that we refer to as control flow hazard. That when I don't know what is my next instruction, when the flow of instructions are not known, we're potentially going to have a problem into our pipeline. Okay? So we need to fix it. And again, you might ask why this wasn't an issue in the single cycle design. And again, in single cycle design, you already finished the instruction all the way. So you finish BEQ, and at the end of the BEQ, you know whether or not the condition was true, and you know the offset plus PC. So now you exactly know whether I should fetch this or fetch this. But for pipeline, since you haven't already finished BEQ and you want to start the next one, you don't know whether this next one should be the taken branch or the non-taken branch, okay? So how do we actually fix this? So I already gave you an example here, so we don't need that. So now the question is, how do we resolve control hazards? Any suggestions? So the answer is forwarding, but what are you going to forward? Whether or not it's 0, you're going to forward it back. But then you'll have that at the execution stage. You want this at the decode stage, right? So you don't have that particularly. But yeah, kind of, you are in the same path. Yeah. Yeah, so the simple thing is you stall until you know, right? So that's always the possible answer. That if you don't know what is the next, we stall, and then once we know, then we continue. Yeah. Exactly. So you can kind of what we call speculation, and that's what we're going to use a lot in this course and generally in computer architecture. So you speculate that, okay, I don't know whether it's going to be taken or not taken, but let's assume one of them, probably not taken because it's easy, it's just PC plus 4. So let's ignore this branch. And if it's really taken, then I need a mechanism to recover and go back and continue. And then if I make this guess correct most of the time, then it's very beneficial, right? So I don't need to stall, I just need to recover. So I'm paying the penalty of recovery versus the penalty of stalling all the cycles. Yeah.
But different read after write hazards because this is just read after write.
Yes, it's kind of like read after write with PC, exactly. That's why it's a hazard, but it's more of a control hazard. It's a little bit more difficult because like all the instructions afterwards is also impacted. So it's not just one instruction, it's like kind of sequence of instructions. But yeah, pretty much the same. Yeah, you had a comment too? Mm-hmm. Yeah, so that's, yeah, exactly. So you can, for example, the simplest thing, the very simple thing you can do is stalling. If you don't like stall, you can, let's say, ignore the branch, continue with PC plus 4, but if something happens, you recover and you take the branch. Great. So let's actually talk about these two solutions, and that's exactly what we're going to do. Let's talk about the stalling first. So the first question is, how many cycles do we need to stall for a branch? Anybody wants to answer that? So if I have a branch equal, based on the design that we provided to you, how many cycles do we need to have until we actually know the outcome of the branch? 1. Why 1? You know, after the execute stage, okay. Any other suggestions? Kind of true. So to actually systematically answer this, there is this thing we call 3 W's. So in order to answer the outcome of the branch, including how long we should stall and what should we do, we need to know these 3 things. The first question is when the branch happens. The second question is where the branch is going to. That is like PC plus offset. And the third question is whether the branch is going to be taken or not, because not all the branches needs to be taken. Okay? So let's actually answer these 3 questions. So when the branch happens, so when do we know that this is a branch instruction? Obviously, we know that this is a branch instruction during the decode stage. Once the controller decode the opcode, it will see that, oh, this opcode belongs to a branch. So we know that this instruction is a branch instruction. So we know somewhere during the second cycle that this is a branch instruction. So somewhere in the second cycle, right? The second question is, where do we branch to? And if you remember, that was PC plus offset. So we need to compute that PC plus offset. And again, if you look into the design, we put this adder here, and then we put this other adder here, right? So we put this other adder in the execution stage. So this is the immediate value, and this was when we had the PC, and this was the offset. So at this point, we have the PC plus offset, which kind of goes to the, so I can either like kind of get it at the end of the execution stage, or in other words, at the beginning of mem stage. Okay, so that's when I know the exact value of PC plus offset. Okay? And lastly, whether or not the branch is taken was this comparator that we have, this sub instruction that we had in the ALU, plus this AND gate that we had with the branch instruction. So remember that we had this 0 flag, and we also had this control instruction that is coming from the controller. So the controller needs to detect that this is a branch. That was equal to 1. Then we AND that with the 0 flag that is coming from the ALU. If this was 1, then my branch was taken. And if you remember, I told you that I moved this AND from here to here because I want to reduce the critical path of my ALU. That's why I moved this add here. So in other words, I know whether or not this branch is going to be taken in the mem stage, somewhere in the middle of the mem stage. Okay? So to kind of like answer all these questions, you will see that I know whether or not this is a branch at the end of the decode stage. I know where I'm going to branch at the end of the execution stage, in other words, at the beginning or at the beginning of the mem stage. And I know whether or not the branch is going to be taken or not somewhere in the middle of the memory stage, so at the end of memory stage. In other words, if I want to know whether this branch, like where is the address and whether this branch, I need to take the max of this, which means that I know the content of the branch somewhere during the mem stage, okay? Either somewhere in the middle or at the end of the mem stage, okay? So going back to the question that I asked, that how long do I need to stall the processor to fetch? Essentially, the idea would be that, let's say I have a branch instruction here and I have a bunch of instructions here. I show them as I1, I2, whatever they are, doesn't matter. And let's say label is somewhere down here. So it's after all of these instructions. So if I look into my pipeline timeline, the branch instruction is going to be fetched. The branch instruction goes to the decode stage. Obviously, at this point, we still don't know whether this branch is going to be taken or not. So I cannot fetch a new instruction. I need to stall the processor. Then my branch goes to the second, to the ALU stage, to the execution stage. At this point, I have this 0, but still I cannot fetch any instruction. I cannot fetch the next instruction either. And then at this point, somewhere at this point, I'm going to have my memory instruction. So here I technically can fetch the instruction. But again, since this is not the beginning, this is somewhere in the middle, I cannot like fetch instruction at the beginning of this stage. So it's kind of like I need to wait until here so that I can safely fetch an instruction. Okay? So in other words, what I'm going to do is that I'm going to fetch the instruction from here. If I know the value here, I can then somehow tell the PC that this is the correct value, and at this point, I'm going to fetch the instruction. So if I looked at this, you will see that essentially I need to stall the processor for 3 cycles, and then at the beginning of the write back stage, I know the answer or all 3 questions that I had, and now I can fetch a new instruction. Okay? So at the write back stage, I can start fetching. And again, how do I stall the processor and all? Same story that we had for load use. I can have a hazard detection unit. I can feed the pipeline with no ops and so on and so forth. Okay? All right, so let's see how bad this is. Okay, so if I stall the processor for 3 cycles, how much performance hit am I going to get? Okay, so let's talk about some numbers, and these numbers are actually coming from kind of average numbers that we see in our benchmarks. Yeah, there's a question. Yeah, so the question is, even if we find that we are not branching, should we stall? Again, if I don't make a guess, right? So the branch comes, I have no idea whether this branch is taken or not taken. I need to wait until I know the answer. If the answer was no, not taken, then I forward. And now you ask this very rational question that why do we even wait if it's not going to be taken? And that's what we're going to do next. That is, let's take a guess. And if this guess is right most of the time, I'm going to save this 3 cycles, right? So that's actually what we're going to do next. Yeah. Mm-hmm. Mm-hmm. So the question is, are you talking about the guessing part? Because for now we are just stalling, not. So the question is about if it takes 3 cycles for us to know what happens during that 3 cycles? There are 2 things that can happen to those. So usually we're gonna just, feed no ops. So no register is gonna be written, nothing gonna happen. Okay. If you make a guess, let's say I'm gonna guess that this is not gonna be taken. And now I'm going to feed this actual instruction into the pipeline. Now you are asking, what will happen if I write to something? And we're going to talk about that. The recovery mechanism is a little bit involved, and we have to be careful. So we're going to talk about that. All right. So where was I? So yeah, we were talking about at this point now I can basically at this point here I can start fetching the instruction. So the answer for the stall is 3 cycles. And let's, as I said, let's talk about numbers. So on average, most of the programs that we write, most of our standard programs that we write, has about 20% control flow instructions. Okay, so 20% of the time, I am stalling my processor for 3 cycles. Okay, and that's a lot of cycles. That's too many stalls in our system. You can actually kind of compute what would be my CPU time for this mix. So in original mix, if you remember, I had IC times CPI times CT. Okay, and as I told you that ideally my pipeline CPI is almost equal to 1. Okay. Now, if 20% of my instructions are 3 cycle stalls, this means that 20% of the time, I no longer have CPI equal to 1. I have CPI equal to 4 because it's 3 cycles and then there's an additional cycle. So then you can kind of like do it this way. Say that, okay, 80% of the time, I have CPI 1 times CT. So 80% of, sorry. So I'm going to have 0.8 times IC times 1 times CT plus 20% of the time of IC times 4 times CT. And that would be my new CPU time, right? So it's kind of a weighted average between these 2 numbers. And you can compute this and you will see that. And then if you like measure the speed up, which is like the old versus new, speed up would be the old CPU time divided by new, you will see that this actually has a huge performance hit just because of the fact that we are stalling by 3 cycles. Okay. So we need to definitely do something about this. And we already talked about like the potential solutions. And that is what we're going to do, and that is being done in most of modern systems. And that is what we call speculation or guessing. So the idea is that there is only 2 outcomes for this branch, either taken or not taken. So let's actually take a guess and continue with that. But then we need a mechanism for recovery as well. Okay? So let's talk about those 2 things. How do we make that guess? And how do we recover the processor from bad things that can happen? Okay? This, by the way, what we call speculation. Okay? Speculation is very, very powerful tool in modern processors that essentially the outcome of a particular event is not known, but the processor does not wait for that outcome to be known before taking actions. This is just one example of a speculation. There are many, many other instances of a speculation, some of which we're going to talk about later in the course. Some of them are more advanced topics that you're not going to see in this course, but you're going to see in more advanced computer architecture courses. But generally, speculation is Happens very, very commonly in modern processors. Unfortunately, speculation also caused lots of security vulnerabilities. Some of you have heard about Spectre meltdown. The cause of those is a speculation. But that's, again, story of another course. But let's see how do we actually make the guess. So now we have two options. We have the option of not taking, and we have option of the take. Okay? Which one should we pick? Which one is the better guess for us? And let's say for now, we're going to do statically, which means that we're going to always guess not taken, or we're going to always take, we always guess taken. Later on, I'm going to introduce what the concept of what we call branch prediction, which we're going to add another unit to our processor, which dynamically decide. For some branches, it's going to guess not taken. For some other branches, it's going to it's going to guess taken. But for now, let's start simple. Let's think that we have static predictor that always output either not taken or taken. Let's see which one is the best. We're going to start with not taken. The reason for not taken is that not taken, it means that we just continue as usual. We just do PC plus 4, PC plus 4. So it has minimal impact on our processor in terms of changes that we need to make. Okay? So if you look at the not taken, let's say if I see this branch, and this branch is in the fetch state, now if I go to the decode stage, and if I want to fetch something, since I don't care, I'm always going to predict not taken, I can then freely let these I1 comes. And then at this point, we're going to see that, oh, this is a branch. That's fine. I'm going to continue, and so on and so forth. And I'm going to let these other instructions to also come into the pipeline. At this point here, we're going to see whether we make the wrong decision or whether we make the right decision. If we indeed was not taken and we predicted not taken, then that's great. Nothing going to happen. My performance immediately improves because I did not stall my processor. But there's a problem here, and that is that what if it's actually taken? What should we do? How do we recover the processor? We're going to talk about that later. Okay? So again, the great thing about not taken strategy is that if it's indeed not taken and the branch is also not taken, then we didn't stall at all. So the performance is not impacted by any form and shape. And again, if I talk about stats, remember I told you that 20% of my instruction mix is control flow instructions. Out of those 20%, 50% of them are 50% of what we call forward branches are taken, and 90% of backward branches are also taken. Okay. So assuming that you have branches could be either forward or backward, and let's say we have kind of equal amount of forward and backward branches. Out of the forward branches, think about this as if then else's or jumps. 50% of the time these branches are taken, and then 90% of the time of backward branches are taken, because these are like for loops and while loops and so on and so forth. Okay, so if you actually plug in the math, you will see that about 30% of all branches are not taken. Okay, and 70% of our branches are actually taken. Okay, and again, if you plug in the math, you will see that 86% of the time we are okay with the not taken approach. Why? Because 80% of instructions are not branch instructions. They are PC plus 4, PC plus 4, so we can continue as usual. Out of those 20% instructions that are indeed branches, 30% of them are not taken. So 20% times 30%, that gives us the 6%. So 80 plus 6, 86% of the time, we're going to have a not taken branch, and we are correct. And now the question is that 14% of the time that we are wrong, what should we do about it? Does that make sense? Does this? Yeah. Great. So now the question is, I'm basically saying here is that only 30% of the time the branch can be not taken. So it seems logical to do taken. The problem with taken is that I need to change a lot of things in my processor, which I don't want to. I'm going to do it eventually, but for now, I'm going to see if I just do not taken, how much does that improve my processor? And the improvement is rather minimal, right? So it used to be 80% and now it's 86%. So 6% improvement in terms of times that we are correct, but still this is very minimal, remember, right? So we don't really change anything. We just continue normally, and that immediately gives us this kind of free 6%. Okay, but you're asking the right question. Why don't we do taken? And we're gonna actually do that later in the lecture. Any other questions? Okay. But before actually talking about kind of these additional changes, let's talk about what will happen if we make an incorrect decision. So in this case that we are talking about, if you're always assuming that the branch is not going to be not taken, if it's indeed taken, then we have a big problem, and that is the correctness issue. It's not a performance issue that you can say that, oh, okay, like we're gonna have less performance sometimes. This is actually a correctness issue that we have to fix. Otherwise, our program is going to run incorrectly. Okay? So in order to fix that, we're going to have this idea calling flushing. So we're going to let instructions to be fetched and go inside the pipeline. But at some points that we realize that we made a mistake, we need to kind of erase them. We need to remove them from the pipeline, and we need to replace them with some other instructions. Okay? This is the idea of what we call flushing. Before explaining what is a flushing, essentially flushing kind of like similar to bubble. So let's have a quick break, and then I'm going to explain how the flushing is going to work. Okay? Moving on. So the problem that we are trying to solve now is that we want to do not taken. And again, the reason that I want to do not taken because it's slightly simpler. So I'm going to do not taken, but then I'll need to fix this very important issue, and that is that if I make a guess whether it's not taken or taken, and then the actual outcome is different from what I've expected or what I've predicted, then I need to fix. And the fixing will happen with this flushing behavior, okay? So how do we flush? Remember, I already told you that we can insert bubble instructions by effectively adding this 0 to the control signal, okay? And essentially what we did was we are adding this mux in the way of the controller, and then we choose whether we want to use the actual signal or whether we want to use the 0 signal, okay? So the idea of the flushing is exactly the same. We're going to replace instructions with bubble if we decide that these instruction needs to be discarded. In forwarding and hazard detection unit, we only had one place that this needs to be done, and that was in the decode stage here. So we only added this mux because, remember, we only needed to stall the pipeline in the decode and fetch stage and let the others go. But for branch prediction, now there are instructions in the execution stage that also needs to be flushed. And then there are other things in the past that also goes more forward, and they also needs to be flushed. As you can see, then what we will do is that now we are adding these two additional muxes, that what they do is they are flushing the instruction that goes to the write back and memory as well, right? So essentially this will make sure that we can get rid of anything past the decode stage if we decided to. And again, as you can see, all of these instructions are generated by the hazard detection unit. So the hazard detection unit is now having sorry, it's not generated by hazard detection unit, it's generated by the control unit, because we know that this is going to be a fetch instruction that needs to be basically, flushing things out. Okay, so if we know that we made a mistake, we're going to flush things out from the controller. And then as you see that we still have these IF flush and write enable for my decode and flush fetch states, because we want to keep those things there for my load use and so on and so forth. So I'm gonna prevent those two states from updating, and I'm gonna replace whatever we fetch in the execution, memory, and write back stage with all zeros. Yeah, question. Mm-hmm. So the question is, what if that you already write to a register? So again, the timing thankfully prevent that from happening. Remember that we know things in the memory stage that whether or not this is taken, and by that time, the previous instruction hasn't reached to the write back stage yet. So they're always like guarded by the branch. So branches in the mem stage, every other instruction is previous. Now the next instruction goes to the memory stage, and now you can flush it out. So bad things happens only in memory stage and the write back stage. Nothing happens in the execution stage or decode stage, all right? Because you're only reading. So since we are always making sure that by the memory stage we know the results, once the branch goes to the write back stage and the instruction is supposed to go to the memory stage, we're going to replace it with zeros. So we're going to prevent things from being written into the memory, and we're also going to prevent things from being written in the write back stage. Yeah. So the question is, do we do 2 bubbles or 3 bubbles? Because the instruction can, so essentially you can have like, instructions that, there are 3 cycles that you need to wait, right? So there are 3 instructions that you need to bubble out. That's why you do execution, memory, and write back. And then so yeah, I'm gonna show you the full picture also as well. So I'm just showing you the control part, but as you can see, it's fairly straightforward that how we do that. And as you can see, that for the decode stage, we have kind of like 2 conditions for flushing. We used to have the condition for flushing because we have a load use, and now we have another condition because of a branch misprediction, right? So that's why this is an OR signal now, that either of those two cause a flush by the decode stage, okay? So again, the timeline, what happens that, to answer the question that you just asked, so if the branch goes forward, right, the branch goes like this, at this point that we know that we made a mistake. But if you look at this point here, I have I3, I have I1 here, I have I2 here, and I have I3 here, right? That's why I need to clear basically 3 things from moving forward, right? And then these things move forward, and I'm going to replace them with the correct bubble as they move forward, okay? So let's talk about what we call branch miss penalty, okay? So what is the penalty of doing this flushing? Again, as you can see that if we make a wrong decision, we need to flush 3 instructions. This is as if that we are stalling the processor for 3 cycles, right? So in other words, the penalty for misprediction is 3 extra cycle of stalls, because although you execute some instructions, those instructions are wasted. You need to get rid of them. So as if that you would just run the no ops from the beginning. So there's no difference. It's actually even worse because now you kind of spend a little bit more power of switching other things. But in terms of the actual performance, miss penalty is exactly the same as if you had stalled the processor. And again, if you remember, for example, if we say that, if for example, if we come up with this arbitrary number that, okay, 70% of the branches are taken, then we are good only 30% of the time, right? So our prediction is great only 30% of the time. 70% of the time, we are unfortunately need to pay this penalty. So it's an improvement compared to stalling. If we were stalling, we were incorrect 100% of the time, right? So remember that stalling alone means that we are paying this penalty 100% of the time, but at least guessing not taken, improving immediately by 30%, right? And if you remember, as I said, 20% of the instructions are control flow. So 20 times 30, we're going to get 6% overall improvement in our performance. Okay? So now let's talk about how do we make this even better. Because obviously there is an opportunity. The first thing that comes to mind is, why don't we predict take-in all the time? That will immediately flip the equation from 30% right to 70% right, right? So the answer for that is can we somehow predict take-in? And in order to predict take-in, we need to know the address of the next. Remember, the address of next instruction for not taken was easy. It was PC plus 4. And I already have an adder in the fetch stage that compute PC plus 4. Okay? So it was great. It was working perfectly well. But now if the branch is not taken, I need to compute PC plus offset. And I need to compute that in the decode stage at the latest, because I need to be able to fetch the next instruction while the branch is in the decode stage. Okay. So again, going back to this where, when, and where, I know that this instruction is branch in the decode stage. That part is great. But there are two other problems that I need to solve. I need to know the where and whether, whether answers to fix this, specifically where, because where is the size PC plus offset. Because remember, I want to be able to, once the branch equals in the decode stage, I want to be able to fetch the next instruction, which is PC plus offset, and put it in the fetch state. Okay. So that's the problem that I'm dealing with now. Okay. So here's what I'm going to do. So I'm going to do this changes in my pipeline design, where the next PC calculation can be moved to the decode stage. Okay. If you remember, in my original design, I was using the PC plus offset as an adder, as a specific adder that kind of takes the PC, takes the offset, and add them together. What I need to do now is I need to move that adder to here. So the first thing I'm going to do is that I'm going to move that adder, which used to be here. Now I move it to here so that I can immediately generate this, this value here. Okay? So that's the first thing I'm going to do, changing my pipeline design where what used to be here is now here. Of course, that means that now the critical path here is going to be extended, so I have to be careful about that. But thankfully, again, since the memory is longer, I can move this here. So that's the first thing I'm going to do. The second thing I need to do is, again, I need to know whether or not this branch is taken, right? So for that, I need to answer this whether question. That is, I need to know whether RS1 and RS2 are equal to each other, or whatever condition that we are making. Okay. So remember that for that, we had this 0 signal, which was happening by the ALU during the execution stage. So here's the trick that I'm going to do. I'm going to add this additional comparator here. Okay. I'm showing it by this equal sign, but consider this as any condition that you can have. So for example, you can have less than or greater than. I'm showing it as equal just as to show that this is a comparator. But essentially what this comparator does is that it takes this value here, this is RS1, and also RS2, and this is the condition whether or not this branch is going to be taken. So basically this will be fed into the controller, and the controller is going to issue whether or not we need to flush things, or whether or not we can continue doing things. Okay. So what I'm doing now is essentially I'm changing my pipeline processor such that I made two main changes. One is I moved this adder to which used to be here to my decode stage. And also I added this comparator, which did not exist. In the past, we were using this 0 signal from my ALU to decide whether or not I'm branching. Now I'm just completely getting rid of that. Oops. I'm getting rid of that zero signal, no zero signal anymore. The zero signal will going to be generated here, and I'm going to feed that into my controller here. I did not show it in this picture, but just imagine that there is a blue signal like going to the controller. Okay? And then the way this works is that now I'm going to be able to basically decide whether or not the instruction that I read is PC plus 4 or PC plus offset, okay? So if it's PC plus, so remember that normally what I do is that this is a branch equal, this is PC plus 4, but now at this point I know whether my branch is taken or not. What I can do is that if I see that the branch is indeed equal, so in other words the branch has to be taken, I will flush this instruction by using this. So I'm going to flush this, and I'm going to provide this correct value so that at the next cycle I'm going to do PC plus offset. Okay, so that's what I'm going to do. So instead of reading the PC plus 4, I'm going to feed this instruction to PC plus offset. So the next cycle I'm going to read PC plus offset. Okay. So again, what I'm doing here is that I'm trying to resolve the branch in the decode state. So I'm trying to reduce the branch miss penalty from 3 cycles to now only 1 cycle. Okay. I still need to flush 1 instruction, but it's much, much better than what we had before, which was 3 instructions. Okay. Eventually, I want to be able to just predict not taken without penalty. But for now, I'm trying to do it at least with 1 cycle penalty. Okay? So these are the changes that I made. I moved this adder from here to here. So this will give me the answer of where. I already know the when answer. So remember, we had 3 questions. The when answer, and I already know this in decode stage. The where answer was where are we jumping to? And this used to be execution stage. And now by changing and moving the adder, I also now have this in the decode stage. And now the answer to whether used to be that and branch with 0. So this was 0, and this was branch, and this was happening in the mem stage. Now I'm moving this by using this comparator here, and then also now move this into the decode stage, okay? So I have the answer of all 3 questions in the decode stage, which means that I can only just waste 1 cycle to be able to do them not taken properly. Okay? So here's the changes that I made. Remember that still we need to maintain some of these flushing things. I'm going to talk about it why later. But so these are the all things that we had in the past. Now I'm just basically making these 2 changes. And all I need to do now is that there is this flushing things that are happening here. Because this used to be PC plus 4. If I decided that this branch is taken, this needs to be flushed and replaced by PC plus offs. Okay? So again, what happens here is that, remember this was BEQ, BEQ, and this was like I1, and then this was I2, and this was I3. And remember, at this point here, that BEQ was in the mem stage, we knew that we made a mistake, so we discard 3 instructions. What has changed now is that with these changes that I made, at this point, I'm going to know what this is the branch instruction and this is taken. So all I need to discard is just 1 instruction. So I immediately replace what used to be 3 cycle penalty with just 1 cycle penalty. Okay? There's one issue with this, and that is what we call raw data hazard. Remember that we had, so let's say, let me give you this example. If I have BEQ, RS1, RS2, RS2, and label. So this works great. But if I have something like this, if I immediately before this, if I have something like add RS1, let me actually give you a real example. If I have like X1, X2 label, And then here I had x1, x3, and x4. Okay? As you can see, there is a raw data hazard between x1 and x1 here. By the way, this is RS1, right? So this is source, but this is destination, right? So there is a raw data hazard here going on, right? Because x1 is being updated in the previous cycle, but then now I'm reading from it in the branch equal. I already told you that I can fix this with forwarding, but the assumption there was that I'm going to forward things here, right? So I was forwarding things in the ALU, in the memory, in the execution operation. But now I need to do this here. Now I need to read things in the decode stage. So forwarding cannot help me with that. Okay? So what should I do? I should go back to the load use problem that I had. So I'm going to stall for one cycle. And then at that point now I know what is the correct value. Then I'm going to continue. Okay? So kind of like to recap, what we are doing is we are essentially doing this idea that actually yes, we are doing this idea that if we have, similar to load use hazard, if you have what we call a branch hazard, where you have a branch instruction, whether it's a branch equal or something like that, and we want to check these two instructions like RS1 and RS2, and then we have an instruction before this that has the RD that's either this one or this one. I need to stall for one cycle and then let the instruction to continue. Okay? Yeah. No, it's just one Y2. Yes. Yes. There is one. So the question is, there is one flush and there is one stall. Exactly. So worst case scenario, you have so in normal scenario, you're going to have one cycle flush. Okay. But now you're going to have one cycle of stalling because of the raw data hazard, and then plus one cycle of flushing because of the misprediction. Questions? All right, let me maybe quickly summarize the things that we discussed. So we started with control flow hazards, okay? We said that the problem with control flow hazard was that I have sequence of instruction and I reach to a branch. Now I have this question that whether I should do PC plus 4 or whether I should do PC plus offset, right? And what I realized, what I need to do is dynamically make that decision, right? Otherwise, I cannot keep the pipeline going. The very first thing I can do is that when I reach to a branch equal, I just stall, okay? So that was my option number one. Then we talked about how many stall cycles do we need, and the answer was I need to answer 3 questions: where, when, and whether. And the answer to those things was that eventually I need to stall up to mem, which means that 3 cycles, okay? That was my original design, that if I reach to a branch and I do nothing, I'll stall 3 cycles and I'm good to go, okay? Then we talked about, okay, how can we make this better, right? So we proposed 2 optimization. The first optimization we proposed was that, how about guessing, okay? And with guessing, we started with guessing not taken. The reason for not taking was that it was easy for us because we just do PC plus 4, BC plus 4. This, I gave you some numbers. This kind of like improve our system 30% of the time, which was good. But then there was the problem with guessing, and that is after 3 cycles, I'm going to realize that I made a mistake. So if we make a mistake, I need to recover, right? So the recovery process was by adding bubbles, right? So we put bubbles into our pipeline, and with bubbles we were able to basically replace any instruction that we want into the pipeline with bubbles. The problem though was that I waste 3 cycles if I make an incorrect decision, right? So the last thing I tried to do was, what if I know the outcome sooner, right? And then we talked about how soon and say that, okay, I want to be able to know the outcome at the decode stage. At the fetch stage, later on, you're going to see that we actually can know the outcome at the fetch state, but it's require lots of other changes that we're going to later talk about. So the fastest that we can know the outcome would be the decode stage. And again, in order to achieve this decode stage, I need to answer the same 3 questions. I already know this, I already know this when part because that's literally the job of the decoder. But I didn't know the answer of this where and whether. The where part is when you need to do the adder. And I said, okay, that seems to be very simple. I just move the adder that I used to have that takes the PC plus offset, and I move that in the decode stage. That's literally what I did here. That's the thing that I did here. And now I also need to know whether this branch is taken or not taken. And that's what I did here. So this used to be here, and now I moved this to here. Okay? So by doing these 2 things, now I know all 3 outcomes of the branch. And what does this, how does this help us? It helps us with basically reducing the penalty from 3 cycles now down to 1 cycle. Okay? So I still pay the penalty of these 30%. So I still do not taken, but at least I change the penalty from 3 cycles to only 1 cycle. Okay? So now my processor is much, much faster because now I can do these things better. And then last kind of piece of housekeeping that we needed to do was this unfortunately creates a new problem to us, and that was the raw data hazard that I described here. So doing all these things, since I'm doing the comparison during the comparison happens during the decode, what used to be fixed by forwarding things to the execution stage no longer works for the decode stage because the forwarding is not happening during the decode stage. So what we do instead is we stall for 1 cycle and then continue doing what we used to do. The other option would have been to move the whole forwarding logic to the decode stage. But for now, let's not talk about that. What we're going to do is we're going to stall for 1 cycle and then continue. Yeah. So the question is, how does stalling would help us? So we're going to, basically what we're going to do is that we're going to replicate the things that we had in the past and these things. So essentially we have 2 options to decide what we're going to do, right? So we're going to, basically once it goes to the, you still have the ALU operation, you still can maintain your 0 flag and all those things. Yeah. And we're going to show you the next time the updated kind of graph. Yeah. Exactly. So the question is, if we have a raw data hazard, we need to stall for 1 cycle and then flush for the next. Yes. Are we good? Okay. So last thing I want to show you is the role of the compiler. Okay. We kind of discussed this while we are describing these things. But compilers can do multiple things, okay, in order to fix the issue of branches. The very important things that, excuse me, the very important things that the compiler can do is what we call a delay slot. And this delay slot can be used for both load use data hazard and control flow data hazard. Remember that with all this optimization, we only need to flush one cycle, right? So what we can do is that in order to prevent even that one cycle, I can, if I have these instructions here, and then let's say I have a branch here, and then I have a bunch of instructions here, and let's say my label is here, and then I have a bunch of instructions, and at some point, you know, there is a jump that this is kind of like the beginning of that D part that I talked to you about, that where that regardless of whether the branch is taken or not, both of them will reach to this point, okay? So this is where the branch is going to converge, okay? So what the compiler can do is that these instructions going to be executed no matter what, right? Whether or not your branch is taken, I can find these instructions and move them up, okay? So if these instructions are indeed independent from the outcome of here or the outcome of here, I can basically move this to the next instruction after the branch, okay? Remember, we have the branch in the decode stage, right? So branch is in the decode stage, and we don't know what to fetch, right? And I said that, okay, we can fetch PC plus 4. If we made a mistake, we discard, we do PC plus offset. But the alternative option is that we don't do either PC plus 4 or PC plus offset. If the compiler can actually bring one of these D instructions here, that is always guaranteed that this can actually work, okay? So the compiler can reorder instructions such that the independent instructions that regardless of the branch can be between the branch instruction and the next instruction. And that way we can always guarantee that we're going to have useful work there. So now we don't need to then flush anything outside my pipeline, regardless of whether the branch is taken or not taken, okay? So that's one optimization that many compiler does. But there are lots of ifs, there are lots of conditions here. We need to find an instruction that is independent. We need to find an instruction that's like both of these converge and so on and so forth. This is not guaranteed all the time. But if I can find such an instruction, I can move it to this what we call delay slot, okay? That's one thing we do. The second thing that the compiler can do is that, remember I told you that not taken happens only 30% of the time, and taken happens 70% of the time. But the compiler can reorder things such that the chance of not taken increases, right? So for example, remember at the very beginning, I told you that I can do something like this, right? So I can put like not taken here and taken here. If the compiler changed the order of these things based on the behavior of the branch, we can increase the chance of not taken versus taken, right? So I can essentially, this is something that that the compiler can decide that whether the taken branch is the one that is happening more frequently versus the not taken one, and then I can reverse this process, right? So that's the second thing that the compiler can do to change the taken versus not taken behavior. Going back down. The third thing that the branch can do, the compiler, sorry, can do is that it can reduce the number of branches, okay? This can happen with what we call loop unrolling, because the problem with loop is that there are lots of backward jumps that are always taken, and that's the big problem with our not taken strategy. If I reduce this for loop, so loop unrolling is this, that, for example, if I have a for loop bunch of instructions and there is a jump back instruction here, right? So what I can do is that if I unroll this loop, which means that if let's say this is supposed to be 10 iteration, I copy this code 10 times, then I effectively remove the need for branches because I just have a straight line code. So I do this one time, instead of jumping back, I just continue. This instruction and this instructions are the same thing, okay? I just unroll the loops, okay? or I can do the same thing with my functions. I can inline my functions. So I remove the need for call function and return functions. If I inline my functions into my main function, then I don't need to do branches. In other words, we just remove the possibility of branches completely so that it doesn't matter how well we are doing with branches. We can improve the performance this way. The trade-off, though, is that unrolling means that the size of your memory increases, because now what used to be, let's say, 10 instructions or whatever, and then we just repeat this by having a loop. Now I have, let's say, 20 or like if I unroll this 10 times, now I have 100 instructions. And this 100 instruction needs to be stored in my instruction memory. In the past, it was just 10 instructions and a loop counter. Now I have 100 instructions without a loop counter. So there is a balance between the size of your instruction memory versus the performance you're going to get from the branch predictor. And again, these are the trade-offs that the designers have. So you can offload some of these works to the compiler so that the compiler can help you in order to increase the speed of the system. Okay? So that's pretty much it. So next time we're going to actually talk about branch predictor in a dynamic fashion. So far, we are just only doing not taken. Next time, we're going to start talking about taken. And this is actually the end of what we need for your quiz 1. So next time, I'm going to just briefly overview all the things that we have learned so far, but no new. So this is basically where you need to know for your quiz 1. Quiz 1 is the Tuesday of the following week. So not next week, the week after. Yeah.